In its very first year of operation, the James Webb Space Telescope found something that shouldn't have been there. Galaxies, fully formed, massive, glowing with the light of hundreds of millions of stars, sitting at a point in cosmic history just 3 to 500 million years after the Big Bang. According to every model of galaxy formation astronomers had, that is not enough time. Not enough time for gas to collapse, for the first stars to ignite, for those stars to die and seed the next generation, for enough generations to pass to build something this large, this bright, this soon. Some of these galaxies appeared to have converted nearly all of their available raw material into stars, an efficiency number that, on paper, is close to impossible. Others had already stopped forming stars entirely, sitting quiet and mature at a point in the universe's history when nothing should be mature yet. Astronomers gave them a name that stuck: the impossible galaxies. And in the years since that first shock, the field has split between researchers trying to explain them within our existing model of the universe and researchers who think they might be the first real evidence that the model itself needs to change. This is Deep Space Declassified. New classified file every week. Subscribe before we go further. Let's get into it. To understand why these galaxies are a problem, you need to understand how astronomers date them in the first place. Light takes time to travel. The further away something is, the older the light we're seeing. A snapshot of what that object looked like when the light left it, not what it looks like now. For the most distant galaxies, that light has been traveling for over 13 billion years, meaning we are looking directly at the infant universe, not inferring it. Astronomers measure that distance using redshift. As the universe expands, light traveling through it gets stretched toward longer, redder wavelengths. And the amount of stretching tells you how long the light has been traveling and how much the universe has expanded since. A redshift of 10 or 11, written as z equals 10, z equals 11, corresponds to a universe only a few hundred million years old. The James Webb Space Telescope was built specifically to see this deep. Its predecessor, Hubble, could see galaxies out to roughly this range, but only faintly, at the very edge of its capability. Webb's infrared instruments were designed from the start to resolve exactly this era in detail. The period cosmologists call cosmic dawn, when the first stars and galaxies were supposed to be switching on. Within months of its first images being released in 2022, Webb had already found more galaxies at these extreme distances than astronomers expected across the telescope's entire planned mission. And a significant number of them didn't look like the young, small, chaotic proto-galaxies the models predicted. They looked evolved. One of the clearest examples is a galaxy called GNZ11. Its light left it roughly 430 million years after the Big Bang, one of the earliest galaxies ever spectroscopically confirmed, meaning astronomers didn't just estimate its distance. They measured it directly from the specific wavelengths of light it emits. And what they found inside that light was strange. GNZ11 showed extreme properties, evidence of unusually vigorous star formation, and a compact, dense structure unlike the loose-forming blobs earlier models predicted for galaxies this young. It wasn't alone. A 2023 study led by astronomer Ivo Lebay, published in Nature, identified several candidate galaxies at redshifts between 7 and 9, several hundred million years after the Big Bang, that appeared to have stellar masses comparable to the Milky Way. A galaxy the size of our own, fully assembled in a fraction of the time our galaxy took to build itself. To reach that kind of mass that quickly, the math requires something extreme. These galaxies would have needed to convert almost all of the available ordinary matter in their region directly into stars, an efficiency approaching 100%. For comparison, galaxies today typically convert somewhere around 20 to 30% of their available gas into stars over their entire lifetime. with the rest staying as diffuse, unignited material. An efficiency near 100%, sustained long enough to build a galaxy this size, this early, doesn't match anything astrophysicists have directly observed happening in a real galaxy before. Researcher Mike Boylan-Colchin, whose independent analysis reached similar conclusions, described the situation succinctly. These results, if they held up, would represent a serious tension with the standard model of cosmology. If they held up turned out to be the key phrase, and this is where the story becomes as much about how science corrects itself as it is about the galaxies themselves. In 2024, a research team led by Nicholas DePrez used new James Webb data from a survey program called CANUX, the Canadian Nearest Unbiased Cluster Survey, to revisit the original claims. Rather than relying on a small number of galaxies from one patch of sky, they used data covering many more regions, searching for objects similar to the ones in the original study. They found 20 candidate galaxies at similar distances, and when they analyzed them using comparable methods, the result was different. These 20 candidates were neither as massive nor as old as the original sample had suggested. The team's conclusion wasn't that the impossible galaxy problem was fake. It was that the original claims, based on a small sample from one region of sky, may have overstated how common these extreme objects actually are. If massive, mature galaxies exist this early in cosmic history, said co-author Adam Muzzin, they are likely far rarer than the first headline suggested. This is genuinely how astronomy works at the edge of what our instruments can measure. A striking early result gets more data thrown at it, from more independent teams using more sky coverage, and the picture sharpens, sometimes in ways that soften the original shock. It doesn't mean nothing strange is happening. It means the size of the strangeness is still being measured. Even with the most extreme early claims walked back somewhat, a real unresolved excess remains, and researchers have spent the years since 2022 trying to explain it without abandoning the standard cosmological model entirely. One leading explanation involves how stars actually form in these early chaotic environments. Rather than a slow, steady conversion of gas into stars over long stretches of time, some models propose bursty star formation, short, intense episodes where a young galaxy rapidly ignites a huge fraction of its available gas at once, then goes quiet, then bursts again. A galaxy caught mid-burst could appear far brighter and more massive-looking than its true average state, an effect called Eddington bias amplified by burstiness. Essentially, we may be disproportionately catching these galaxies at their brightest, most extreme moments. A second explanation involves the stars themselves. Modern star formation tends to produce a predictable mix of star sizes, the initial mass function. But in the metal-poor, extreme conditions of the very early universe, some researchers propose a top-heavy initial mass function, meaning early star-forming regions may have preferentially produced more massive, more luminous stars than we see forming today, which would make a young galaxy look brighter and more evolved for the same actual amount of stellar mass. Both explanations share the same basic idea. The early universe might simply behave differently than the nearby universe we've spent a century studying, in ways that don't require new cosmology. Just better models of star formation physics under conditions we've never directly observed until now. Not every researcher is satisfied with explanations that stay entirely within star formation physics. A smaller but serious contingent argues that at least part of the impossible galaxy problem points towards something upstream, in the cosmological model itself. The standard model, lambda CDM, makes specific predictions about how quickly structure should grow in the early universe, based on the properties of dark matter, dark energy, and the initial density fluctuations left over from the Big Bang. If galaxies are consistently forming faster and bigger than that structure growth prediction allows, even after accounting for bursty star formation and top-heavy stellar populations, it suggests something about the growth rate itself may be off. Some of the same theoretical proposals that come up when discussing the Hubble tension resurface here. Early dark energy, a hypothetical component that behaved differently in the universe's first few 100,000 years, has been proposed as a way to accelerate early structure formation, potentially helping to explain both the impossible galaxies and the mismatch in expansion rate measurements with a single adjustment to the model. That's speculative, but it illustrates something important. This isn't an isolated puzzle. It's one of several places where precision cosmology, over the last 5 years, has started finding results the standard model didn't clearly predict. And researchers are increasingly asking whether these separate anomalies might share a common root cause. The story gets stranger with a specific category of object: galaxies that formed fast. In 2023, a team led by Tobias Lusser identified a galaxy that had already become quiescent, meaning its star formation had significantly shut down at just 700 million years after the Big Bang. For a galaxy to build up a substantial population of stars and then quiet down that early requires an entire life cycle of formation and shutdown to have played out in a fraction of the time such processes normally take. This matters because quiescent isn't the natural early universe state models predict. Young galaxies are supposed to be actively forming stars. Quiescence is usually associated with older, more evolved galaxies that have used up or expelled their star-forming gas after billions of years. Finding it this early means whatever mechanism causes galaxies to stop forming stars, feedback from supermassive black holes, gas expulsion from intense star formation itself, or something else, was already operating at a stage of the universe when nothing was supposed to be old enough to trigger it. It's a second related impossible galaxy problem. Not just galaxies growing too fast, but galaxies living an entire evolutionary arc. Birth, growth, shutdown, on a timescale that compresses processes normally measured in billions of years into a few 100 million. There's a third thread tangled into this same mystery, and it involves black holes rather than galaxies. Alongside the unexpectedly massive early galaxies, Webb has identified supermassive black holes at redshifts of 7 to 10, sitting at the centers of galaxies from this same impossibly early era, with masses exceeding 10 million times the mass of the Sun. Growing a black hole to that size requires either an enormous head start, an extraordinarily fast growth rate, or both. Standard models of black hole growth, built around gas accretion at rates limited by radiation pressure, struggle to produce black holes this massive, this early, without violating known physical limits on how fast matter can fall in. Some researchers have proposed that these early black holes may have started from unusually large seeds, collapsed massive gas clouds, or more exotic origins, rather than growing up gradually from the remnants of dying stars, the conventional path for black hole formation. The impossible galaxies and the impossible black holes may not be two separate mysteries. Some models suggest the black holes could be accelerating structure formation around them, or that whatever produced unusually large initial seeds for one also explains rapid, efficient star formation for the other. Neither piece is fully explained on its own. Together, they paint a picture of an early universe considerably more active and considerably faster to build large structures than the standard model anticipated. It's worth pausing on how quickly this entire field has moved. Before Webb launched, the impossible early galaxy problem barely existed as a mainstream research topic. A few papers using Hubble data had flagged early hints of tension, but the sample sizes were too small and the distances too uncertain to draw strong conclusions. Within about 18 months of Webb's first images, it had become one of the most actively debated topics in observational cosmology, with dozens of research groups publishing competing explanations, reanalyses, and rebuttals. That speed cuts both ways. It means genuinely surprising results can reach the public before the field has had time to fully stress test them, which is exactly what happened with some of the earliest, most dramatic Milky Way-sized galaxy at redshift 9 headlines. But it also means the correction process happens fast too. The 2024 CAN-US reanalysis came less than 18 months after the original claims it was testing. This is precision cosmology functioning as intended, even when it's messy in the moment. Bold claims, rapid scrutiny, revision, and a narrower, more defensible picture emerging from the process. The current consensus isn't that the early universe is calm and predictable after all. It's that it's genuinely more active than expected, just not always to the degree the very first headlines suggested. So where does that leave the standard model of cosmology? Not broken, but under real pressure from multiple directions at once. The impossible galaxies, the unexpectedly massive early black holes, the Hubble tension. Each one, individually, might have a mundane astrophysical explanation involving star formation physics, selection effects, or measurement subtleties. But researchers increasingly ask whether treating each tension in isolation is the right approach, or whether the accumulating pattern of the early universe did things faster than predicted is itself the signal. Lambda CDM remains by a wide margin the most successful cosmological model ever built. It correctly predicts the cosmic microwave background structure, the large-scale distribution of galaxies, and the abundance of light elements from the Big Bang with extraordinary precision. None of the impossible galaxy findings overturn any of that. What they do is mark a specific edge, the earliest few 100 million years of cosmic history, as a place where the model's predictions and the observations don't yet comfortably agree, and where the explanation might be new astrophysics, refined cosmology, or some combination neither camp has fully worked out yet. In its first years of operation, the James Webb Space Telescope looked back further than any instrument in history and found galaxies that on paper shouldn't have had time to exist yet. Massive, evolved, in some cases already finished forming stars, all within the first few 100 million years after the Big Bang. Some of the most extreme early claims have since been narrowed by better data and wider surveys. But the core puzzle hasn't disappeared. Galaxies built faster than expected, black holes grown bigger than expected, a universe that in its earliest chapters appears to have been considerably more productive than the models built before Webb's launch predicted. Whether the explanation lies in stranger star formation physics, unusual initial stellar populations, black hole seeds we don't yet understand, or an adjustment to the cosmological model itself, the answer is still being actively worked out. One survey and one reanalysis at a time. We are, right now, watching astronomers rebuild part of the timeline of the universe in real time using a telescope that keeps finding things the previous generation of theory didn't predict. Do you think the standard model needs to change, or is there a mundane explanation we just haven't found yet? Leave your take in the comments. And subscribe, because the next classified file goes up in a week.